everyone and welcome to chapter number 7 in the three-phase induction machine course, Induction Motor Design classes. Let's start. In this chapter, we are going to define the NEMA design classes A, B, and C, and D, and we are going to explain the difference in torque speed curves for each class, and we are going to relate starting torque, starting current, and slip to each class. Still, we didn't understand what they mean by the class. We are going to cover that one through this video. Once we finish the video, we are going to understand or use the NEMA class knowledge when designing or specifying motors in technical documents. Also, we are going to select the appropriate design for a specific application. We're going to wrap up this chapter or this video by a quick quiz to know how to select or choose a design class. Let us ask ourselves this question. Can one induction motor handle every application? I'm not speaking here about the power. Definitely, there is one application requires something like 5 horsepower, another application requires 100 horsepower. I'm speaking here about the application nature. For example, I have here a pump, that one is mechanical pump, and another example here, something like this rotating bridge. Can I use one induction motor here and there? So assume that we have the same power. The answer is definitely no. So definitely there is one motor suitable for the pump, another motor is suitable for this rotating bridge. And this is why we have different design classes. Let us see. Let me remind you about the machine construction. The machine consists of a stator and rotor. Stator has slots and rotor has slots, and these slots is filled with bars for a squirrel cage induction motor, for example. So we are going to highlight some facts here. The size and shape of the rotor bars and slots determine the operating characteristics. Also, open slots have the effect of reducing the permeance of the slot leakage path, hence reduce the leakage reactance, but at the same time, the magnetizing current is increased. Closed slots decrease the magnetizing current but increases the leakage inductance. So this means slot shape and size was going to affect the motor parameters. And if you remember from the previous chapters, if the rotor resistance, for example, is increased, the torque characteristics will be different from the normal rotor resistance. Accordingly, three-phase induction motors are standardized according to generally accepted criteria. And this criteria is established by the National Electrical Manufacturer Association, NEMA standard. And this is why we have different motor classes. And each class is suitable for specific or certain applications. What we see here is the normal torque speed characteristics we had in the previous chapters. So we have a starting torque, we have maximum torque, and the developed torque. So these torque speed characteristics could be suitable for application like this pump. So if this pump is not frequent starting motor, so we can use these torque speed characteristics. We have a certain starting torque, we have maximum torque and developed torque. But the question, can we use the same torque speed characteristics for application like this one, which is London Bridge? The answer is definitely no. So we need a high starting torque and we need a low speed. So definitely there are different torque speed characteristics. The typical torque speed characteristic curves with NEMA design classifications A, B, C, and D are as shown in the figure. As you can see here, for the blue line here, we have class A, we have a starting torque, we have a maximum torque, and we have the stable region so the machine can operate in this region. Regarding class B, the starting torque is lower than class A by a small value, and the maximum torque is smaller than the maximum torque of class A, and we can operate in the same region as well. For class C, we have a high starting torque, but the starting torque is the maximum torque. So this point is not the maximum torque, we call it the stall torque or breakdown torque. And the machine operates in this region as well. So class C is specified by high starting torque, high speed. But class D, high starting torque, which is the maximum torque, and this is the stability region, so the machine can operate at low speeds or high slip. So looking for this table, the class A has normal starting torque like this one, and definitely class B has normal starting torque because they are close, but class C they have high starting torque and class D is high starting torque as well. Regarding the current, class A has a normal current, which is something like 6 to 8 or 6 to 9 times the full load current. We are going to see that one in the next slides. But compared to class A, classes B, C, and D has lower starting current. Regarding the slip, Class A has normal slip and definitely B and C, so they are in this region, so the machine can operate at high speed, but Class D is operating at low speed. We are going to look for them one by one. Class A. As shown in the figure here, we have the blue line, we have starting torque, maximum torque, and the motor operates in this region. That one is a Class A. So what are the features of Class A? It has large bars near to the surface, as shown in this figure. It has relatively low resistance and reactance, so this means the starting current is almost high, 6 to 8 or 9 times the full load current. The starting torque is with full voltage is near twice the full load torque for smaller sizes and poles motors. For large motors in size and number of poles, the starting torque is almost 1.1 to 1.5 the full load torque. The full load slip is within 5%, 1%, 2%, up to 5%. Such motor can be used for fans, pumps, compressors, and conveyors, which has low inertia, or we can say low inertia applications. This design is not used for frequent starting because we have high starting current. And also for motors higher than 5 horsepower, it requires a current limiter at starting. So let's conclude the Class A. So starting current is 6 to 9 times the full load current. Starting torque in the range of 1.1 up to 2 times the full load torque. The range of the slip is within 5%. That one is not suitable for frequent starting applications and can be used for fans, pumps, compressors, and conveyors, or any low inertia applications. Class B. The Class B as shown in the figure in the red curve, which is identical to Class A, except that the starting torque and maximum torque is lower a bit. So what is the difference between Class B and Class A? Their cages are characterized by high reactance, low resistance rotor bars that extend deeper into the iron, and they call it deep bar rotor, as we can see here. This design has low starting current, 5 to 7 times the full load current, and compared to the Class A is 6 to 9 times. So these motors are designed such that they can start at full load. Compared to Class A, the starting current is too high. Similar to Class A, the starting torque is almost 1.1 to 1.5 the full load torque, and the full load slip is similar to design A within 5%, and they use the same application or can be used for the same application such as fans, blowers, and pumps. So what is the difference between B and A? If we have one application not requiring frequent starting, our choice should be Class A. But if we're going to have start and stop, frequent start and stop, our choice should go towards Class B. Class C. The Class C is the green curve here. We have maximum torque at starting, and we have stall torque here, and the machine operates in this region. What are the features of Design C or Class C? So the Design C combines the features of both Design B and Design D. So we know B, but we didn't cover D yet. So it has maximum torque at starting. So it's characterized by high resistance with low reactance at the surface. As we can see here, the slots consists of 2 parts. So this part is characterized by high resistance with low reactance at the surface, and low resistance with high reactance at the deep bar. So they call this machine as a double cage rotor. So this type has high starting torque because we have high resistance at starting. So as if we increased the resistance to the rotor. So we have high starting torque, almost 2.75 to 3 times in some cases the full load torque. But the starting current is 5 to 7 times the full load current, which is similar to Class B. And the full load slip is within 5%. But the maximum torque occurs at starting when S equals 1. So the applications for this design class, something like crushers, compression pumps, large refrigerators, conveyor equipment, textile machinery, any application requires high starting torque and high running speed. If you remember in the previous chapter, I said that for slip ring induction motor, we can have maximum torque at starting if we add external resistance. But we cannot do that one for squirrel cage because the rotor is closed. There is no access to the rotor. And we need to find another technique. So the other technique is to use another class, something like Class C. And Class C gives us the option to have maximum torque at starting, and we have a high running speed. What about Class D? The Class D, as you can see here in this figure, we have the light blue curve or the paid one. So we have a maximum torque at starting, and all of this region is a stable region because the maximum torque is a still torque in this case. So what are the features of Class D? Such motors are provided with a high resistance low reactance rotor bars, as we can see here. So we have a high starting torque. Bars are close to the surface, giving the motor a high starting torque with the low starting current like Class C. So we have low starting current, but the difference here that the full load slip varies between 5% to 20%. Maximum torque occurs nearer to the locked rotor torque, so that one is the locked rotor torque or still torque, so that one is the maximum torque. These motors are used for applications such as bulldozers, shearing machines, punching machines, stamping machines, opening gates, and so on. So any application requires high starting torque and the running speed is required to be low speed. Let's take an example. 3-phase 220 volt phase RMS 50 Hz 4-pole star connected induction motor is used to drive a water pump in a residential building. So this means that we know what the nature of application. The motor operates on demand and has the following parameters: R rotor, X equivalent, and the full load slip is 5%. As a maintenance engineer, determine the appropriate NEMA motor design class for this application. So you have one task here. You are going to solve the problem to find the starting current, starting torque, maximum torque, and full load torque, and you are going to check the values. So you need to refer to chapters 2 and 3 videos to know how to calculate these values. So we know from the problem or the data that the synchronous speed is 1500 RPM. The synchronous speed, angular synchronous speed is omega s 157.1. And we're going to use the second approximate equivalent circuit because we don't have R core and XM in this problem. So we have the rotor current or stator current in this case will be 12.77 ampere. And the rotor current at starting is 75.2 ampere. Motor torque at full load is roughly 53 Newton meter. And motor torque at starting is roughly 92 Newton meter. So the motor full load slip is 5%. He said that. This is number one. So we are going to exclude Class D because the motor is running by high speed. So still we have A, B, and C. So let's look for the ratios. The ratio between starting current and full load current is 5.9. So that one could be something like B or C, it depends. The ratio between starting torque and full load torque is almost 1.73. So definitely Class C is avoided now. So we are between B. Some people can say A, but the starting current is 5.9. So there's another reason that I'm not going to use Class A. So the application is a water pump. And that one is a residential area. So that one is on demand. So on, off, on, off. So definitely Class A should be avoided. So the recommended design class should be Class B. Example number 2. Suggest the design class for the following applications. Number 1. Tunnel ventilation fan. So for this application, we need a high speed. So definitely Class D should be avoided. We are in Class A, B, or C. And that one is not a frequent start or stop. And we need a normal starting torque because the machine is going to run at full load. So that one is going to have a high speed and that one is a fan. So definitely could be a Class A or B, not Class C. And are we going to choose A or B? So because that one is not a frequent starting, so we can choose Class A. So for that one, I'm going to choose Class A. But if you choose Class B, is not wrong, but you are going to sacrifice by some starting torque and maximum torque. Let's go for the second application. Rotating bridge. So you need a high starting torque, but at the same time, this bridge is heavy building, so you cannot run that one at a high speed. So definitely you need a low speed, so that one is directly Class D. For another application like that one, shopping mall lift. So we have here a lift up and down, so that one is on demand, start, stop, start, stop, start, stop, and we need a limited starting current, so definitely we are going to have a Class B in this case. We don't need here a high starting torque. Let's look for another application like that one, supermarket fridge. So we need for that one a high starting torque because we need to higher torque for compressing the gas, but the machine should run by the normal speed. Running by normal speed and high starting torque is definitely class C. What will I watch in the next video? We are going to wrap up this course by induction motor quiz. So next video will include a quiz for induction motor. See you in the next video.